Good morning to all. In this video, we are going to discuss about impulse turbine. Okay. So now we are going to study the impulse turbine, study of impulse turbine. So to construct the velocity diagram of moving blades, we are assuming with certain terminologies like, so we are assuming a single stage impulse turbine. A single stage impulse turbine means it consists of only a fixed blade and one ring of movable blades. Okay. Now we are assuming certain terminologies. CBL. CBL is nothing but linear velocity of moving blade. What is linear velocity means? Whenever the high jet stream strikes the moving blade, it will travel certain distance. The distance is known as linear velocity of the moving blades. Okay. Next, C1. C1 is nothing but velocity of the steam entering the moving blades. C0 is velocity of the steam leaving the moving blades. CW1 is nothing but velocity of whirl at rotation at the entrance of moving blade. That is a rotation, velocity of rotation at the entrance of moving blade, which is a tangential component of C1. Okay. Next is CW0, which is the velocity of whirl at exit of moving blade, which is the tangential component of C0. Tangential component of C0. And CF1 is the velocity of the flow at the entrance of moving blade, which is axial component of C1. And CF0 is the velocity of flow at the exit of the moving blade, which is the axial component of C0. Okay. And CR1 is the relative velocity at the entrance of the moving blade, and CF0 is the velocity of flow. As I said, CF0 is the velocity of the flow at the exit of the moving blade. So CR1 is the relative velocity entrance of moving blade, and CR0 is the relative velocity at the exit of the moving blade, and beta is the angle of discharge steam making with the tangent of the wheel at the exit of the moving blade, and alpha is the angle with the tangent of wheel at the steam velocity C1 entry is known as nozzle angle. Alpha is nothing but nozzle angle with nozzle angle, and theta is the entrance angle of moving blade angle at the entrance, and phi is the exit angle of moving blade, Okay. So here the steam jet issuing from the nozzle at velocity of C1 impinges a blade at an angle of alpha. So from the nozzle is arranged with an angle of alpha. From that angle, the steam with velocity of C1 hits impinges the moving blade. Okay. So now, the tangential component CW1 it determines the work on the blade. So the axial component CF1 however does no work but causes steam flow. Okay. So CF1 will help us to determine the flow of the steam, and CW1 will help us to determine the work developed on the wheel or turbine. Okay. So now we are constructing the velocity diagrams of the moving blade. So this is the velocity diagram, inlet velocity triangle and outlet velocity triangle. So see the inlet velocity triangle, the nozzle angle is alpha with the moving blade, and C1 is the velocity, and CF1 is the axial component, and CW1 is the tangential component of the C1, and CR1 is the relative velocity of C1 and CF1, which makes the nozzle angle is the moving blade angle is inlet angle is theta, as is similarly the outlet angle is phi and discharge angle is beta, and CR0, CW1 and CW0 and CR0, CF0 are represented in the inlet and outlet triangles. Okay. So now combined velocity triangle. So now we are making a combined velocity diagram of both inlet and outlet triangles. So in this diagram, the alpha, theta, phi, beta all are represented. Okay. Now force. So from Newton's law, we know that force is equal to mass into acceleration. Mass into acceleration. Okay. So here the acceleration is nothing but change in velocity. Change in velocity. So here the CW1 is the work generation. So therefore force is equal to mass into velocity CW1 minus CW0. So we know that work done is nothing but force into distance traveled. So force developed is m into CW1 minus CW0, and distance travel is linear distance traveled is CBL. Therefore, the work done can be taken as mass into CBL into CW1 plus CW0. Why you are taking CW0 plus CW0 means, so the CW0 is in flows in negative direction, hence we are taking always it is negative, therefore we wish to get work done as MCBL into CW1 plus CW0. So we can rewrite the CW1 plus CW0 as CW. Okay. So now what is the work done on the blade? So work done on the blade is found to be change in momentum of steam jet during flow over the blades. So whenever the kinetic energy, whenever the steam flows over the blades, then the change in the momentum of the blade determines the amount of work done. Okay. As I said, from Newton's law, force is equal to mass of the steam into acceleration. Work done is equal to force into distance traveled, and power developed is the force into distance traveled. Okay. Now, so force on the wheel. Force on the wheel is mass into change in velocity, that is m into CWL, and work done is m into CBL into CW1 plus CW0. That is the work done on the blade. And next is power developed per wheel. So we know that power developed per wheel is nothing but work done by 1000, that will get in kilowatts. Okay. So what is work done? Mass of the steam into linear velocity into CW. C is nothing but summation of CW1 plus CW0. Okay. So now the blade efficiency. The blade efficiency is nothing but ratio of work done on the blade to the energy supplied to the blade is nothing but kinetic energy. So what is the energy supplied to the blade? The energy supplied to the blade from nozzle is kinetic energy. Therefore, the formula for kinetic energy can be taken as half into mv square. Half mv square by 2. Half mv square. So now in the numerator, the work done on the blade or wheel is ms into cw into cbl. In denominator, we can take it as half mc1 square. So from that, if numerator, the denominator will come to numerator, then we used to get it as 2 mscw cbl by mc1 square. That is nothing but the blade efficiency or velocity diagram efficiency. Okay. Next is stage efficiency. Okay. The stage efficiency is nothing but the ratio of work done by the blade per kg of steam to the total amount of heat drop. Okay. So during the expansion of steam in the turbine, there is a pressure drop takes place. Pressure and heat drop will be takes place. That amount of pressure and heat drop is determined by using change in the enthalpy. Therefore, the stage efficiency is equal to work done is CBL ms into CBL into CW divided by H1 minus H2. So here, if you consider mass is equal to 1 kg, as in the stage efficiency is set by work done by blade per kg. So per kg means mass is 1 kg. Therefore, if your mass is 1 kg, then work done will become CBL into CW and divide enthalpy drop H1 minus H2. Okay. So this is the formula to determine the stage efficiency. Next one is, what is the axial force on the wheel? So as I said, force is equal to mass into axial acceleration. So axial forces are here CF1 at the inlet and CF0 is at the outlet. Therefore, we can take it as mass into CF1 minus CF0 or the axial forces. Okay. Now the axial force on wheel must be balanced or must be carried by thrust bearings. So whatever the axial force developed by the steam, that axial force has to be balanced. Otherwise, there is a tilting of turbine maybe happens if over axial force is exerted. So now next one is energy converted to heat by blade friction. Okay, so by means of friction, how much of energy is converted by the blade friction is equal to loss in kinetic energy during flow over the place. So loss in kinetic energy is can be determined by m into loss in kinetic energy can be determined by using formula m is equal to C R1 square minus C R0 square. So C R1 and C R0 are relative velocities at the inlet angle and relative velocity at the outlet angle. Okay. So by using these relationships, we can determine or analyze the impulse turbine. Thank you.